Hi, my name is Emily Diana, and I'm speaking to you today about my recent work, Multiaccurate Proxies for Downstream Fairness. This is joint work with Wesley, Gill, Michael Kearns, Krishnaram, Kenthapadi, Aaron Roth, and Saeed, Sharifi-Malvajerdi. So algorithmic fairness has been featured quite prominently in the news as of late. We've seen some reports of automated resume filtering tools that appear to be throwing out resumes that have certain gender terms in them. We've also seen a lot of discussion about some criminal recidivism algorithms that are just much more likely to keep an African-American man from getting bail than a white man. And we've also seen some nasty cycles with predictive policing where when the police are allocated algorithmically, when more police are allocated, more crimes are caught and reported, and this cycle can cause, can be kind of like a self-fulfilling cycle that makes things worse. So in the literature, we've also been seeing quite a rise in popularity of fairness. So we've had some early papers just studying kind of fairness in the data and looking at the issue where a lot of these kind of negative consequences that I described on the previous slide are not necessarily because of human malice. They can just be things that naturally pop up from the data, from how it was collected, from any kind of current trends that are in the data. So that's been studied. We've also seen some work that has kind of pushed back against the idea that in order to make something more fair, we actually need to not use a protected attribute. So we found that mathematically, it was often better to take that information into account. We've seen the work on Compass, the work on the kind of some of these gender issues. We've had conferences pop up such as FACT, which we are speaking at today, and ACSIncome. And throughout this, there are lots of challenges that are being discussed. So currently, one of the big issues is deciding what types of fairness definitions to use, how to decide what actually constitutes harm, when should we intervene, so at the data collection stage, in the algorithm training stage, perhaps in the deployment stage, and how should we balance trade-offs that often occur in this type of work. So when we make an algorithm more fair, it might become less accurate in a given sense. So the work that I'm talking about today is motivated by a dilemma. We often might want to train a model that is fair with respect to some attribute, but we might not have access to that attribute. So we might want to find a resume filtering tool that is fair with respect to gender, but in the data that we have, we can't actually view gender. So this could be for legal reasons or for policy reasons. And we thought about how can we make a model fair with respect to race if we don't have data about race. So in the 10 or so minutes remaining, I will go through our framework, main result, key insight, experiments, and a discussion. So here's an overview of our framework. So we're imagining a setup where we have a data domain. Omega is divided into features or non-sensitive features X, label Y, and sensitive feature Z. Z we're treating as a K binary vector. So it has K entries indicating membership in K groups. And each of those entries is 0 or 1. We're going to consider a setting where we actually have two learning stages. So we have a proxy learner who actually gets access to data with a sensitive attribute. They're going to produce a function that someone later can use downstream to kind of impute or come up with some reasonable estimate of the sensitive attribute such that when they use that estimate when training a machine learning model, they can have a good sense of whether that model is fair. So more specifically, our proxy model class, we're going to call it script G, is going to map the non-sensitive features to some real value. And generally, we'll have a different function for each of the case-sensitive attributes. So I'll just talk about generally functions that map to one real number. The proxy itself will be chosen from this model class. And it'll have these K components, so predicting each of the different sensitive attributes. And then we'll have a downstream model class. So that might be the resume filtering model that we eventually want to train to do some machine learning task, and we want it to be fair with respect to gender. So the proxy learner aims to find a proxy Z hat such that if a downstream learner trains a model H that is fair with respect to Z hat, then H is also fair with respect to Z. And here in this diagram, again, we see the first stage, the proxy learner gets access to Z. So you could imagine this is some like small group that gets access to some proprietary data. They get access to the non-sensitive attributes and label. And from this, they spit out some function. Now, everyone downstream no longer gets to see the sensitive attribute, but they can see this function and the non-sensitive features and the label. And from that, they'll try to train a fair model. Okay, so one of the key insights in this work is that proxies can and should be real valued. So we kind of looking at earlier literature and just from some examples that we worked out, we found that a binary proxy is generally not going to be informative enough to actually ensure that a downstream learner can train a fair model H. So what we did is we rewrote this quantity, which I'm just going to use as an example of a kind of statistical fairness metric, so the probability of an error given group membership. We wrote it as a ratio of expectations. And notice that on the left, we're looking at the probability that there's an error given that you're in group K, and the probability that there's an error given that you're not in group K. But on the right, we can plug in any real number for ZK. So now this lets us reformulate our fairness constraints in terms of these real value numbers. So kind of the high level idea here is that we want it to be the case that if we satisfy this equation, so if we can find a proxy Z hat such that this ratio of expectations with the true value is equal to the ratio of expectations with the proxy, then it follows that if a model is fair with respect to Z hat, it is also fair with respect to the true attribute Z. And from this, we develop a proxy definition. We say that Z hat is an alpha proxy for Z if for all classifiers H in script H in all groups K and K, these two ratios of expectations are sufficiently close. So the first one, this ratio for Z minus the ratio for Z hat should be within alpha. And again, you can kind of think of these as conditional probability. So the probability that there's an error given that you're in some group. And in the case of these real values, it'll be kind of like weighted conditionals. So once we have that, now we can rewrite everything as a linear program. So we can minimize some objective. We are kind of just choosing to minimize mean squared error here. This might give us a sense that we're trying to make Z and Z hat more similar, but really you could choose any objective here. So we're going to minimize some objective subject to the constraints that the average value of Z on the error points is going to be similar to the average value of Z hat on the error points. And these constraints are multi-accuracy constraints. So we want a Z hat to be an unbiased estimator for Z on the set of points where H errs. So now I'm going to show some experiments that we did. We simulated a downstream learner, and we trained a fair model to be fair. We trained a model to be fair with respect to 4 representations of the sensitive feature and evaluated its performance. So the 4 representations we had were the true labels, Z, baseline proxy, which was a logistic regression of Z on X. What we call an H proxy, which is the solution to this linear program, but without any objective. This is kind of most true to the proxy definition. So our only goal is to satisfy these constraints. And the last one is that program with the mean squared error objective that I showed. So here's an example of an experiment that we ran. And I chose this one partly because it shows an ideal performance. So here we are looking at the ACSIncome data set. So this is very similar to the adult data set, but it's drawn from this kind of superset of census data. And the sensitive attribute here is race. So the y-axis is error disparity. So we want this to go down. The x-axis is error. So we want this to be closer to the origin. So in general, kind of anything towards the lower left is going to be better. So we see that when we train a model to be fair with respect to the true label Z, it is Pareto dominating all of the other cases. When we no longer are able to use the true labels, then the next best thing is to use this H proxy, which is a proxy function that is trained just to equalize those ratios of expectation. After that is the similar linear program where we, in addition to asking that the true Z and the proxy have the same average value on error points for any given predictive model H, we are also aiming to minimize mean squared error. So that does slightly worse than the H proxy in general. And then a baseline proxy does quite a bit worse. So this is a positive result. We see that the similar relationships hold in the test case. Here's another example where we see much less of a disparity. And in fact, we actually see here that the baseline proxy, so using a logistic regression of Z on X as our standard for the sensitive attribute, that actually did a bit better than when we solved the linear program with the added mean squared error objective. Now, when we didn't add that objective and we just train the linear program to satisfy this multi-accuracy constraint, then that still tends to outperform the baseline proxy, and we see good generalization. This is the same data set, but age is used as the sensitive attribute, which we thresholded at 40. So in summary, we found that it's possible to efficiently train proxies that can stand in for missing sensitive features to effectively train downstream classifiers subject to a variety of demographic fairness constraints. The results crucially depend on the assumption that the data that the proxy learner uses to train its proxy are distributed identically to the data that the downstream learner uses. And some questions that we have from this work that we might like to look in the future, for one, kind of this question of what type of objective function to use. So we may want a proxy that's non-disclosive in the sense that we don't want it to be too close to Z. So how do we do that? And then also just in general, kind of what happens if this assumption that the data that the proxy learner uses and the downstream learner uses is slightly different? That's an interesting question, and it's very relevant because in practice that will certainly happen. So thank you very much. I would love to take questions offline. You can contact me, and have a great conference.